Hello everyone, this is Aminur Rahman and welcome to the PhysX project. We are going to start a new video series today to discuss wave phenomena like diffraction, superposition and interference. This one is the first video of that series where we will discuss wavefronts and rays. Let's start. Now what is a wavefront? To understand this, let us check a video first. What you see here is a ripple tank. A ripple tank is basically a transparent shallow water tank with a projected light on it. There is a motor at one end connected to a wooden bar. The motor generates vibration, which in turn causes the wooden bar to vibrate and generate water ripples in the tank. Now let us deal with a diagram of this to understand what we are dealing with. A wavefront means a set of particles. Those are vibrating in sync or in phase with each other. Now, if you look at this diagram, you can think that there are hundreds of waves parallel to each other. These are shown as blue lines in the diagram. They are generated at the left end of the ripple tank and moving towards the right end. On these waves, we can take this set of points to be in sync or in phase. Look at each of these points. Every one of them is at their topmost position of vibration. So they are in sync or in phase. Now, if we connect them with a line, that's a wavefront. We can find such points here again at the next crests. If we connect them all with a line, that's the next wavefront. Similarly, these and these. Important thing to remember is distance between two consecutive wavefronts is a wavelength. Now, because of the projected light from above, we will see shadows here on the white screen below the transparent tank. Such straight and parallel wavefronts are called linear or plane wavefronts, and this distance between them is a wavelength. Now we could find particles in sync with each other at positions other than the crests too. For example, these yellow points at the troughs are in sync with each other too. All of them are at the bottommost position of their vibrations, so connecting them will give us a wavefront too. We generally draw dotted lines to connect troughs. Similarly, here and here. We can show these lines here on the white screen as these. And this distance between them is also a wavelength. Now let us discuss circular wavefronts. To understand it, let us check a simulation first. Think of water drops falling at constant time intervals into a water container. It would look something like this from the top view. Now let's check the 3D view. It would look something like this. Let us freeze the frame here and discuss based on the image. Again, a wavefront means a set of particles. Those are vibrating in sync or in phase. In these waves, we can take this set of points to be in sync or in phase. Look at each of these points. Every one of them is at their topmost position of vibrations. So they are in sync or in phase. Now if we connect them with a line, that's a wavefront. We can find such points here again at the next crests. If we connect them with a line, that's the next wavefront. Similarly, this and this. Such circular and concentric wavefronts are called circular wavefronts, and the distance between them is a wavelength. Now we could find particles in sync with each other at positions other than the crests too. For example, these points at the troughs are in sync with each other. All of them are at the bottommost position of their vibrations. So connecting them will give us a wavefront too. We generally draw dotted lines to connect troughs. Similarly, here and here. One important thing to remember that the circles are not waves. Instead, each circle is made up of lots and lots of waves all traveling outward at the same time. To see how it works, take a look at this marching band. As a group, they form circles that slowly expand outward. We are going to watch again. Only this time, pay attention to the movement of a single individual. What you will notice that each individual person marches in a straight line. It is only when we see a lots of them moving together, then we see the circular shape. The ripples in a pond are very much like this marching band. Lots of individual waves begin in the center and move in perfectly straight lines outward. However, if seen collectively, that group of individual waves forms a circular pattern, which is called wavefront. Same goes for other types of wavefronts as well. Now is the perfect time to explain ray. A ray is simply a line showing the direction in which wave energy is traveling, and rays are always perpendicular to wavefronts. So when you were watching the marching band, direction of each individual person marching in a straight line outward was the direction of a ray. So these are the rays. In the ripple tank, the rays point horizontally, perpendicular to those straight parallel lines. So these are rays. In circular wavefronts, the rays point radially outward, perpendicular to each circle. So these are rays. The shape of the wavefront changes, the source changes. The medium can change, but rays are always perpendicular to wavefronts. That never changes. Now everything we just discussed in the ripple tank, that's all 2D. Top-down view, flat water surface, but the real world is 3D. So let's scale this up. Consider that point source dropping into water to be in 3D, a pulsating sphere, like a vibrating ball. And those circular wavefronts? They become spherical wavefronts, expanding shells, one inside the other, like layers of an onion. The rays point radially outward in all directions, like spokes of a wheel, but in 3D. Now let's check this diagram. In diagram A, close to the source, the wavefronts are visibly curved. But as you move farther and farther away, look what happens. The curvature decreases, the wavefronts flatten out, and at a very large distance, they become essentially flat parallel planes. These are plane wavefronts, shown in diagram B. Same rays, but now all seem parallel to each other. This is exactly why we treat sunlight as plane wavefronts. The sun is 150 million kilometers away. By the time that light reaches us, the spherical wavefronts are so enormous, they are indistinguishable from flat planes. Alright, let's wrap this up. Wavefronts are simply sets of points vibrating in phase. They come in 3 types: linear or plane, circular, and spherical. Linear wavefronts come from straight bar dipper, flat and parallel. Circular wavefronts come from a point source in 2D, like a ripple in a pond. Spherical wavefronts are the same idea in 3D, expanding shells from a pulsating point source. And at a very large distance, spherical wavefronts flatten into plane wavefronts. Rays show the direction of energy travel, always perpendicular to the wavefronts, always. And the distance between 2 consecutive wavefronts? That's your wavelength. Now that's my time for today. Thank you for sticking around. See you in the next video.